Hi, I'm Changsu from POSTECH. This video is for CGO 2021 conference, and the topic of this presentation is Thread-Aware Area-Efficient High-Level Synthesis Compiler for Embedded Devices. Let's start. These days, as our living environment becomes smart, embedded devices are everywhere. For example, in this environmental monitoring example, there are embedded devices that measures various numbers around and they send the collected data to the cloud. They are in charge of various functions and accordingly use various peripherals. And they are also connected to a network. Such embedded devices are already available on the market in various forms. As embedded device market becomes competitive, design time becomes important. Processor candidates to design embedded devices are as follows. In the case of general-purpose processor, it has low efficiency while programming for handling peripherals and threads is convenient. In the case of FPGA and ASIC, hardware design cost is expensive instead of having good efficiency. Therefore, in order to overcome the time-to-market problem, many manufacturers have adopted and used the general-purpose processor. However, using a general-purpose processor brings bad performance, both in silicon area and energy efficiency. The main functions of embedded devices are peripheral management and thread management and data processing. The CPU performs only these three simple roles using a large area and causes a lot of power due to the nature of the embedded devices that is constantly turned on. In the case of ASIC, a lot of area can be saved because it is manufactured with only necessary functions. However, the high hardware design cost is a problem, but which can be solved by high-level synthesis. The general hardware design flow is as follows. The first step is to do software modeling and test in high-level language, and based on this, the programmer manually writes HDL code that performs the same function. At this time, a high-level synthesis compiler can help with this step, so reducing hardware design time by 2 to 5x. High-level synthesis is automatic conversion of behavior on timed descriptions into hardware that efficiently implements that behavior. But in order to use HLS to build a processor for embedded devices, there are functions that the HLS must have. First, HLS tools should build embedded devices with very low area. Second, HLS tools should support multi-thread programming. Third, HLS tools should support peripheral drivers. But existing HLS tools do not satisfy this. So even if HLS is used for embedded device design, there is a problem that programmer must manually write HDL code a lot. Programmer must write all these orange colored parts, device drivers, thread management codes, and control paths to connect processing units. On the other hand, the proposed HLS supports thread and peripheral APIs, so programmer can use them to complete hardware design through C and C++ programming only. Some existing HLS frameworks adopt a soft processor to manage thread and peripheral devices. However, Since this soft processor consumes considerable area, so it is not efficient to use a soft processor only for management. Since the proposed HS automatically inserts the management logic, there is no need to use a soft processor. So the proposed HS saves lots of area. This can make harder design to add more functionalities for resource budgets such as FPGAs. In the case of ASIC, we can save money for this area. The general HS steps are usually divided into 3 steps: resource allocation, scheduling, and binding. The resource allocation steps specify the hardware resources that will be necessary, so resource allocation steps has a lot of influence on the hardware design area. For example, let's apply HS to the following program. In the allocation step, if the allocation step allocates 2 add operator, then each operator will be matched to 2 add operations. Accordingly, the final design consumes 2 operators. On the other hand, when allocation steps allocate only 1 add operator, then 2 add operations have to share the operator. Therefore, the final design consumes only 1 operator, but additionally increase state and consumes the sharing costs such as MOX. Although the allocation step is very important to hardware design area, the allocation step of existing HS tools has some problems. In the existing HS, it is difficult to manage inter-procedural resource constraints because resource constraints are only applied for each function. Even if we use pragma for resource constraints, it is applied only to the function that use the pragma. Also, the existing HS has a fixed circuit topology and designs hardware in a fixed way. There are 2 main types of topology: nested and flat. Nested topology hierarchically instantiates functional units, and flat topology instantiates each module only once at the same hierarchy. So nested topology consumes a lot of area because it is highly likely to generate redundant resources. On the other hand, flat generates only one resource, but if the sharing cost for this resource is large, then we cannot ignore the sharing cost. So we propose a dual HS framework that addresses all these problems. Dual supports thread and paper management automatically by providing APIs for threads and papers. Also, Duo minimizes the overall hardware design area by adding a step called architecture builder. First, let's look at the Duo HS, how to support thread management without general purpose processor. Duo automatically generates FSM by inserting functions for thread management and automatically inserts the thread management modules. For example, in the case of thread creation, it receives a thread ID and executes thread instance based on the ID. Unlike function call, stays continuous without waiting for return. When the thread instance is terminated, the thread is a listener, which is always waiting for receiving the thread ID, and the thread join synchronized based on this listener module. Since threads cause multiple flow, so contention must be managed for the shared modules. So DuroHS automatically inserts arbiter and contention management logic for shared modules. Since DuroHS does not use a soft processor and automatically inserts management logic, hardware design area can be reduced. And Duro proposes a new circuit topology to further reduce the area required for processing. This architecture example is a design for wearable devices. When using nested topology, a lot of redundant resources are generated and they occupy an area. In the case of Plaque, even if resources are generated only once, it consumes a lot of area due to the sharing cost, such as contention management. On the other hand, the proposed circuit topology applies the appropriate allocation policy for each resource unit. When Duro HS allocating operators, Duro considers three policies for each operator type. Policy 1. The private policy assigns one operator per a user module. So each user module has their own operator and is sharing within a data path of each function module. And policy 2, the sharing within thread policy assigns an operator per thread. So user modules within the same thread share the operator like this. And policy 3, the sharing between thread policy assigns an operator for all user modules. So private policy may have a high operator cost but a low sharing cost. On the other hand, in the case of sharing thread between threads, the operator cost is low while the sharing cost may be high. DuroHS calculates the area cost of all policies and determines the policy having the minimum area. To build a memory architecture, several memory management methods can be used. However, memory analysis fails and the compiler does not know which memory object a memory access should access. Then, if so, we must conservatively manage all memory modules in only one centralized memory controller. If memory analysis can find all memory access targets, then we have two options. DuroHS considers whether to manage memories shared between threads in a centralized or decentralized manner. DuroHS calculates the area cost of each memory management and determines the policy having the minimum area. Both management allocates a private memory which is used by only one thread without arbiter. For evaluation, we designed 6 embedded devices based on DuroHS framework, and the devices uses various papers and performs various processing algorithms. To evaluate area efficiency of our DuroHS framework, we implement Vivado HS-based modules which add hand-coded management logics and Nancy circuit topology and flat circuit topology. We use Synopsys design compiler with the 45 nano cell libraries for ASIC evaluation. In ASIC area result, Duro HS compiler reduces the area by 28% and 13% compared to Vivado HS and flat topology, while the latency required to perform each event did not increase. As the area is reduced, static energy consumption also decreased. So, Duro HS compiler reduces the energy consumption by 25% and 9% compared to Vivado HS and flat topology. We also evaluate the latency and energy consumption of FPGAs and general-purpose processor. FPGA programming was based on our Duro HS compiler, and FPGA Spartan 6 reduces latency and energy consumption by 62% and 51% compared to Arduino Uno, which is a hardware platform generally used in embedded devices. Thank you for listening.